current session, in the previous session, we were actually discussing the generalized version of the central limit theorem, this theorem, which goes by the name of central limit theorem. And I was actually reading the statement of the theorem when suddenly the time was actually over. So the statement goes like this: let x1, x2, xn be the sample from a population having mean expectation of xi equal to mu. Suppose we have n samples, and these are the random variables associated with these n different samples, in such a manner that expectation of this random variable x1 is the population mean mu, expectation of x2 is also the population mean mu, expectation of xn is also the population mean mu. That means x1 is the point estimator of the population mean, x2 is the point estimator of the population mean, xn is the point estimator of the population mean. If it is so, and if the variance of xi is sigma square, okay, variance of each of these variables are sigma square, then for large n, if you increase the size of the sample, the random variable x1 plus x2 plus dot 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 xn will approximately have a normal distribution. If these are the normal variable, these are the variables. See, they have never said that x1, x2, xn are normal random variables. They have only said that these things, if this thing happen, their sum total will be a normal random variable for large n, such that expectation of these things will be, expectation of this sum will be expectation of x1 plus expectation of x2 plus expectation of xn n times. So we'll get n mu. And variance of x1, x2, variance of x1 plus x2 plus xn will be, variance of x1, variance of x plus y is variance x plus variance y when x and y are independent. And here indeed we are talking about the independent samples. So this will be variance of x1 plus variance of x2 plus dot 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 plus variance of xn. And n terms are there. So we get n sigma square, or standard deviation of x1 plus x2 plus xn will be sigma root n. So this theorem is very important. What this theorem is saying, it is also very important. You have to understand this. This theorem is saying, first of all, try to see that they haven't said what sort of variables are these. Is there you may ask various questions. Is x1 a discrete random variable? You never know. They have not said. If x1 is a continuous random variable, I don't know. Is x1 a binomial variable? I don't know. Are they normal random variables? We don't know. But if you keep on increasing the size of the sample, their sum total will be approximately normal. So it is said, it can be derived, many other results can be derived from this central limit theorem. The ultimate point of the central limit theorem is that if you increase the size of the sample, then almost every distribution tends to follow normal distribution. And therefore, I'm spending a considerable amount of time in teaching you the normal random variable. It is so important. This binomial, this Poisson, everything tends to follow normal distribution when you keep on increasing the size of the sample. And the important part, which I hadn't told you yet from the very first class, and I was waiting for this central limit theorem to be introduced, is that if you can remember, I told you that if n is very large and p is considerably small, very, very small, then binomial distribution tends to follow Poisson distribution. Binomial tends to follow Poisson. What I didn't say is that when n is very, very large, but p is not that small compared to the size of the sample, then p is a significant figure. It is not too small, but n is too large as you can make it. Then binomial distribution tends to follow normal distribution. It's a condition under which binomial distribution tend to follow normal distribution. But but central limit theorem, we already have known that almost every distribution, under the condition that the sample size is increased, they tend to follow a normal distribution. It's a very important theorem, and central limit theorem is often asked in the examination. You have to memorize these expressions and this statement, okay, into as a whole. Now let's move on to, and this ends the note of class 9. Let's move on to the next note, which is class, I can say that according to my name, it's BSM 201 class 10 note. Anyways, this note is actually related to the central limit theorem and sampling distribution, where I have discussed a very interesting problem. Okay, so let's study the problem. First of all, let's see what is it saying. An astronomer is interested in measuring in units of light years the distance from her observatory to a distant star. However, the astronomer knows that due to differing atmospheric conditions and normal errors, each time a measurement is made, it will yield not the exact distance, but an estimate of it. As a result, she is planning on making a series of 10 measurements and using the average of these measurements as her estimated value for the actual distance. If the values of the measurements constitute a sample from a population having mean d, which is actual distance, and a standard deviation of 3 light years, approximate the probability that astronomers' estimated value of the distance will be within 0.5 light years of the actual distance. Now, remember to begin with, let me tell something about this astronomy and probability. Remember, just for your kind information, that probability and normal, specifically the studying of normal distribution, actually started from astronomy, and the astronomer who actually did a tremendous amount of work on this was known as Tycho Brahe. I don't know whether you have heard his name or not. Tycho Brahe was the astronomer who actually introduced normal, not in the shape as now it is being studied, but the concept of that. In Tycho Brahe's days, this word normal may not be there. I don't know. I'm a little bit confused whether he introduced the word normal or not. But the observation, the physics the measurement, the observations, the physics he actually applied has resemblance with the normal random variable which you had studied. Okay, it's just for your information, because you have to know the history in of the society, of the situation under which a particular theorem or theory were actually invented. Now, an astronomer is one important thing is also written over here. Carefully observe. The astronomer knows that due to differing atmospheric conditions and normal errors. What do you mean by this word normal errors? Is there anything like abnormal errors? No. Normal errors means you are associating a random variable associated with the error. You are trying to calculate a distance between 2 points. Say, for example, geometrical. Think about a 2-dimensional point, and the points are such that now you see one thing I can say. Let us not move on to the cosmos. Let us move on to a sheet of paper, and I am putting 2 dots, like say for example this and this. We all know that these 2 are points, and Suppose I'm actually interested in finding the distance between these 2 points, capital A and capital B. Okay. Now you can take a scale, you can measure the length of this, and you can say the distance between the 2 points is this much with some units indeed. But an intelligent boy, he may make me confused. He will say that, sir, well, what you have drawn is not a point actually. Under the magnifying glass, this point looks like a circle. Okay, so actually you have not drawn the point. You have actually, under the magnifying glass, I am actually finding this. So where is the point? So I said, oh, okay, yes. So, okay, now take this too. Now he has also increased the power of his magnifying glass and says, sir, it is also a circle. Now, actually, the definition of point is actually axiomized. We do not know what point is. We just say that it is the two dots that we have marked on the board, but point is actually not defined, cannot be defined, because we even do not know today what point is actually. It doesn't have any definition. We say, to convince ourselves, we say that it is something which has no shape, size, and like this thing. But under the magnifying glass, it has a shape, its length, breadth, everything under the magnifying glass. So it is not. So this is the difference between the thought process of a mathematician and then a thought process of a physicist. Okay. Now, mathematicians have more freedom than the physicist. Okay. So anyways, I'm not going into the debate of that. Now, when you are doing this, and you are every time you are making me confused, and I'm trying to reduce the size of my points again and again. Now, what I actually make will be, you'll observe that every time I do this, and you take a fine scale, a scale with fine markings on it, and you put them at one end of the scale on a point A and another end of the scale on point B, and you find the distance. Every time we'll get a different distance, and it has to be. It has to be. And if you keep on increasing this particular experiment again and again and again and again, and if you say, for example, you are hitting at a certain distance at a certain point, and you say that I want to reach that distance, or you can say, sir, please guess what can be the distance between A and B. So I'm saying that the distance between A and B looks like it can be approximately 4 centimeters. And every time you are getting 3.97, 3.98, 4.1, 0.1, 4.2, where the limiting process is actually coming. Now, if you find the distance that you have measured each time with my presumed distance, you will find a kind of value, which is the difference between the two, actual distance and the calculated distance, or estimated distance and the observed distance. And if you say that this is the error, sometimes it is large, sometimes it is small, sometimes it is positive, sometimes it is negative. And if you go on increasing the experiment to a certain amount of time, okay, then you can associate to each values of these errors, you can associate a random variable, and you will say that, okay, this is the error, this is the random variable associated with the error in my measurement of this of finding the distance between the 2 points, capital A and capital B. And if you keep on increasing for large n, remember, for large n, if you keep on increasing these things again and again, you will get a tremendous amount of values, errors of this but simple experiment which I'm telling you right now. Now, if you plot the figure, and if you get a bell-shaped curve of these error terms, if you get a bell-shaped curve like this, okay, what you will say that my errors are normal. My probability distribution of the errors which I have obtained satisfying the normal probability law, and therefore they have said these errors are normal errors. So you have to understand what do we mean by normal errors, because this understanding is very important. And each time a measurement is made, it will yield not the exact distance but an estimate of it. As a result, she is planning on making a series of 10 measurements and using the average of these measurements as her estimated value for the actual distance. Now, if the values of the measurements constitute a sample from a population having mean d and a standard deviation of 3 light years, approximate the probability that the astronomer's estimated value of the distance will be within 0.5 light years. Now, you see, you can, if I give you some time and I tell you that, yeah, central limit theorem will play an important role over here, you can immediately, you can give a little bit of effort to find the solution. You can immediately find the solution. Finding solution is important, but before you find solution, I'm again repeating, before you find solution, understanding is also very important. Okay, so that understanding, for this understanding, we actually this understanding can only be discussed in the class. Okay, and if there is no class, you learn it, you discuss among with your friends. He will give his thoughts, you will give your thoughts, and then okay, in this manner you can learn things together. Now let's find out how they have solved this particular problem. The probability of interest is indeed this one. We are actually trying to find the probability that this difference x bar is the average of x minus the actual distance. This difference is lying between minus 0.5 and plus 0.5. The astronomer estimated value of the distance will be within 0.5 light years of the actual distance. If you read this line again and again, they are actually interested in finding this probability. Now here x bar is the sample mean of the 10 measurements. X bar has mean d and standard deviation 3 by root over 10, where I applied the theorem that I talked about in the previous session. This probability should be written in terms of the standardized variable capital Z x bar minus d by 3 by root over 10. So our only job here, if you want to bring Z in between minus 0.5 and plus 0.5, so you have to just divide the thing by sigma by root over n. Sigma is the variance, standard deviation, and 10 is the sample size. So you know what particular result I'm using over here. And if I do so, now rest is just a calculation. I'm not going to repeat the things because you have already known. I have already discussed these things elaborately in my previous sessions. So I to be very brief, you see, I have divided the entire all the sides by 3 by root over 10, and 3 by root over 10 is a positive quantity, so the inequality is not changing, and we are getting points minus 0.527 and plus 0.527. Now, as I told you, each time you do a problem related to normal distribution, it is better to draw a normal curve. So I have drawn the normal curve, and I'm interested in finding the probability of the region lying between minus 0.527 and plus 0.527. Now this region, okay, I think a little bit of mathematics will be required because you are studying it for the first time. Now, so this is your z equal to 0, and that is your minus 0.52, and suppose this is your minus plus 0.52. We are interested in finding the area of this portion. Now, area of that portion can be found. How can we find this area of this portion? See, look at this. If I can find the area of this region, if I can find the area of that region, if I can add the two areas, this is area 1, this is area 2. If I can add the two areas and I can subtract it from 1, because 1 is the total area, then I will get the required M. Then I will get the area under consideration. So that's why that has been written over here. But now again you see that my curve, the drawing which I am making right now, it's a very horrible drawing. So I beg pardon because my drawing is very bad actually, because anyways, it is a horrible normal curve anyways. Anyways, so what I have this point now, minus 0.52 and plus 0.52. I want to get area of these two halves. Now you see one thing, that how can I find the area of these two? Because we know the table which I am showing here below, this table has been taken from the original table which I showed you in the previous session. It is the table representing this, the probabilities where z is less than x. Okay, now I have taken the section, I have considered the section of for 0.5 only, because I am interested in 0.5, and all the column headings have been written over here. So 0.52 will obviously be equal to this one. If I'm interested in 0.52, that will be this one. 0.527 is approximately equal to 0.53. So I can consider this also. If I consider this, I'll get a probability 0.70. And if I consider this, I'll get a probability of 0.69. Now, how can I take the help of this table to calculate this thing? Now you see, since this is a normal curve, the area of this portion and area of that portion, they are actually equal. So this half can be written as twice probability of z greater than 0.527. Why? Because this and this half are their same. And by the complementary probability, that is probability of a bar equal to 1 minus PA, we can write it as 1 minus twice into 1 minus probability of z less than 0.527. And there, from this probability can be found from either this or that. Okay, so that has been done. This calculation has been done. We just give a little thought, you'll understand what has been done to calculate the probability. I'm erasing whatever I've written. I'm erasing because if I scroll down, this will be carried forward. This rough work will be carried forward and will block our view. Hope you have understood. Hope you are understanding. I hope you have been understanding since the first day of the class of related to normal random variable. Now, oh, this is there, still there. Now you see, so after calculating this, what we have found is that the probability is coming out to be 0.4038, and our conclusion is that we see that with 10 measurements, there is a 40.3% chance that the estimated distance will be within plus or minus 0.5 light years of the actual distance. I have shown here another example. Now in this example, only thing I would like to say is that what is happening. I would like to tell that this particular problem is a problem where I have not, you can see if you read this problem, you'll find that here central limit theorem, in the previous problem, that is the astronomer's problem, central limit theorem has not been used. But in this problem, the central limit theorem will be used. So it is a problem of central limit theorem. Question number 2 is the problem of central limit theorem. And you can say the question number 1 is the problem of sampling distribution only. I am actually asking you to go through the problem by yourself after the class, or when you will be studying the things, you read this question, you'll understand what is the difference between the question, between the two problems set in question 1 and question 2. I am not going to explain this thing. I am leaving it out for you. If you face any difficulties, so you can text me. We'll be discussing this problem in the next class. Because I think that this particular problem will not be required any discussion, because you can understand why it is the problem of central limit theorem. I can only give you a hint. See, look at this word total yearly claim. Now, total yearly claim means if you consider the claims of the person to be the variable xi, total yearly claim will be x1 plus x2 plus dot 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 plus xn. And we do not know whether these yearly claims are normal or not, but we know that if I keep on increasing the sample size, they become normal. So this total, when we talk about total of random variables, actually we have to consider the central limit theorem, which has been explained in the given problem. You just read the problem, you'll understand it. It's a very beautiful problem also. It is not only thing I can say that this problem is not related to physics. Now this problem is related to marketing management. Okay, so because the book from which I'm selecting the problem, it's made for everybody, not for only physicists. And another problem which, okay, now after this problem, another definition I have used over here, but I'm not going to talk about this definition now because the morning video, the morning session, the video of which I uploaded in the YouTube, I know that you have not gone through the video. You have seen the you have only seen the second video. You have given a glimpse of the second video only, but you have not gone through it totally in its totality. So I'll recommend you to go through all the videos of the normal random variable uploaded so far carefully tonight, and then we are going to study the second section of this particular note on. I think at this point I have to be a little bit slower because the things are actually very new, and you have to give some amount of time to understand what is happening. So today I'm not going to stretch my class any further. I'm going to end my test session today. Also, I have not taken my lunch and I'm actually starving. So I'm going to conclude my today's session. Tomorrow we are going to meet in our schedule. Oh, sorry, tomorrow we do not have any class with. I do not have any class with you. I will have class with CSC section A. Anyways, there I will discuss the second section of this particular note, and you will have a significant amount of time to go through all this. Okay, so with this I'm going to conclude my today's session. Hope to meet you in the next week in our scheduled time. Till then, bye.